Morning, everyone. Come on in. How are we doing? Questions while we wait? So Benjamin's asking any note-taking tips. Well, I mean, in a typical class, that's what you should do. Take down everything that's done. In this course, I mean, you can do that. There's no issue. In fact, that's probably what's going to work best for everyone. So if you want a general approach, then that's the approach. Now, some people might do better in a different way. So I mean, I'm going to leave that up to you. But for a course in general, that's what I would do. That's what I did when I was an undergraduate student. You know, take down the notes, and then after class, reread those notes, and then do some exercises. Show that let's try this question out. Very good. Let's try this. Show that this function has at most one root in the interval -2, 2. Notice that they're not, I mean, it's easy to read too much into that. They're not asking you to show there is a root. There might not be a root. It's asking you to show there's at most one root. So let's suppose the opposite. Suppose we have two roots. Suppose we have two roots where A is the smaller of the two. Right, so if we call this P of X, P as in polynomial, then P of X is continuous on the interval AB, differentiable on the open interval AB, and P of A is equal to 0, and it's also equal to P of B, right? I mean, that's the definition of a root. So by Rolle's theorem that we saw last time, there exists, let's call it C1. I don't want to use C. I've already used it here. It's a different C. There exists a C1 in the interval AB such that P prime of C1 is equal to 0. Right, so there exists a point where the derivative is 0. Well, what is the derivative? P prime is what? It's 3x squared minus 15. If we factor out a 3, it's x squared minus 5. And what are the roots? The roots, easy to see that it's plus or minus root 5. And root 5 is bigger than root 4, which is 2. So this is 2 point something or negative 2 point something. Which is outside of this interval. Contradiction. So an assumption we made must have been wrong. And the only assumption we made was that we had 2 roots. There it is. How are we doing here? Questions? We do not test for one root, right? I mean, you have to be careful as to what the question is asking. Here the question is asking to show there's at most one. There might not be any. That's going to be very dependent on what C actually is. If C is very large, this is never going to be 0 in that interval. What would we do if we had a 3rd degree case where we couldn't solve the roots? Well, you would somehow have to argue that that 3rd degree polynomial was never 0. Do we always use Rolle's theorem for these problems? Well, again, you know there's never and always. But maybe you want to think about using Rolle's. All right. Last time we were looking at the mean value theorem. Why don't we recall the mean value theorem, right? We saw that it was a direct consequence of Rolle's theorem. Really, it's really a generalization of Rolle's, if you will. Let's recall what the mean value theorem says. And today we'll see how do we prove this question. We came up to a contradiction here, right? The roots were outside of the interval minus 2 to 2. So an assumption we made must have been wrong, and the only assumption we had made was that we had 2 roots. So there can only be at most 1. What about 3? I don't know what 3 you're talking about. This 3? What about 3 roots? Well, right, what about 3? If you have 3 roots, then you must have had at least 2 to begin with. right? So restrict your attention to 2 of them, and we're in trouble again. No, nothing. We don't know about the midterm. I mean, people are grading it as we speak. It's tremendously long to grade. So we'll see. If we get it done by next week, that would be very nice. Can we try to find the other root? What other root are we talking about here? Right, our function, in fact, didn't have 2 roots. In fact, it might not even have any roots. Mean value theorem. Let f of x be continuous. I'm just restating it here for convenience. So continuous on that, differentiable on the open interval, and differentiable end. Then there exists C in the open interval such that f of b minus f of a over b minus a is equal to f prime of c. Can we try to find out, will they be complex numbers, but still, right, so I mean, when we talk about roots here, we of course mean real roots, absolutely. And perhaps that was not specifically stated in the question, but I think it's understood. All right. So that's the statement of the mean value theorem. We didn't find any roots, correct? Correct, and the question wasn't asking us to find roots. The question was asking us to show that there's at most 1 real root. And like I said, it's easy to read too much into the question. So you want to be careful. You don't want to do too much. You just want to do what the question is asking. And it was asking us to show there's at most 1 real root, which we did by assuming we had 2 and coming to a contradiction. So this is the mean value theorem. Today we're going to look at a few consequences of the mean value theorem. The first one, you know that the derivative of a constant, you know what the derivative of that is, right? The derivative of a constant is 0. Question, are there other functions whose derivative is always 0? What if you had a function whose derivative was 0? Can you conclude that that function has to be constant? So claim, conversely, if the derivative of a function is always 0, right, so the 3 equal signs mean identically 0. It's always 0. It's 0 for all values of x. If the derivative is always 0, then f of x is constant. Let's prove it So the proof is nice and easy. It's just a simple application of the mean value theorem. Take an x for proof. Let what do I want to call it? Let y be in the interval AB and apply the mean value theorem to the function f on the interval AY. What do we get? Then f of y minus f of a over y minus a is equal to f prime of c for some c in the interval AY. But your derivative is always 0. So this is 0. Multiply both sides by y minus a, and we get f of y minus f of a is 0. Or f of y is equal to f of a. That's the claim, Benjamin. The output is always a constant function, is always the same constant number. Kamal, where did I lose you? Right, so what are we saying here? We're saying that for any value of y, f of y is equal to f of a. So f of a is the constant value of your function. Right? No matter what value of y you choose, it's always equal to f of a. Come on. Question? Right? You know the derivative of a constant is 0. Here I'm suggesting the converse. If your derivative is always 0, the function had to be constant to begin with. We just multiplied, right? First of all, f prime is 0. So you have this. Multiply both sides by y minus a, or cross multiply. Why was f of y chosen? What I want to show is that for any value in here, f at that point is going to be the same as f of a. F of a never changes, so f of y never changes. We just multiplied, cross-multiplied, Maxwell. Cross-multiply. If f is a constant, how can we find f of a? Well, you know how to do that. That's trivial. Take an example. If f of x is 3, what is f of minus 1? It's also 3, exactly that. Does that necessarily prove it, or just that f of y and f of a are equal? Well, I mean, it proves that f of y and f of a are equal, but y, you can choose any value you want. right? So I mean, if you had A and B to be 1 and 2, if you choose any value in here, you get the same as f of 1, right? So your function at 3/2 is the same as at 1. Your function at √2 is the same as what it is at 1, and so on. All the values of your function are the same as what they are at 1. Your function doesn't move. The y in f of y really means the same as the x. Absolutely. So the function is constant, as Kamal mentions. Absolutely. So what have we seen? We've seen, you know that if, you know the derivative of a constant is 0, and so now we have the converse. If a function has a derivative which is always 0, it had to be constant to begin with. Now let's ask the question, what if you chose two functions that had the same derivative? What can you conclude then? Suppose you have two functions which share the same derivative. Then they have the same shape. What does that mean? Then there exists a constant C such that f of x is the same as g of x plus c. Well, same degree, Matt, you're thinking polynomials, but it doesn't have to be polynomials, right? I'm suggesting that if two functions have the same derivative, then they have to differ by at most a constant. Exactly, right? But that's in the case of polynomials. What if you had other kinds of functions? That's what we're saying. They're just translated vertically, or they differ by a constant. Let's prove it. The proof is nice and simple. And it follows immediately from what we proved just a moment ago. Let's define a function, h of x, to be f of x minus g of x. Since these two functions are continuous, exactly right, Aiden. This is why, for those of you familiar with the antiderivative, this is why when you find the antiderivative, you get a constant c. Matt is introducing a new definition there. Nothing wrong with that. It's interesting. It certainly has some merit. But what about sine x? Right, what about sine x? What would the degree of sine x be then? Right, yeah, then we run into some problems. So if we define this function, then h of x is continuous on the closed and bounded interval, differentiable on the open interval, right? Because both f and g are. And what's the derivative? What's the derivative of h? Right, Shamir? Thank you. The derivative of h is the derivative of f minus the derivative of g. But the derivatives are equal. So this is 0. The derivative is 0. What does that mean? You have a function whose derivative is always 0. So from the previous claim, you know that h had to be constant to begin with. Ella, the issue with differentiable on the closed interval, you know, well, I mean, it's the same issue as with continuity, just a bit worse. I mean, with continuity, you know that you need limit from the left and limit from the right. Here at the left-hand point, you cannot take a limit from the left. But we circumvent that issue by just referring to the limit from the right. However, with continuity, you still have that same issue. Because I said continuity, but I meant with differentiability. The derivative, you still have that same issue, right? Because the derivative is itself a limit. So you need to be able to approach from both left and right. And it's a convention that we usually don't talk about left-handed derivatives and right-handed derivatives. We do so for continuity, not so much for differentiability. So as Kamal mentioned, h, whose derivative is always 0, h must therefore be a constant, but that h is f of x minus g of x. So immediately f of x has to be g of x. Let's see. Or their difference, they can only differ by at most a constant. How are we doing here? Right, so this is very nice. You know that if two functions differ by a constant, then their derivatives are the same. And now you have the converse. If their derivatives are the same, they had to differ by at most a constant. Let's do a few examples from the book. Similar to the first one we did. Show let's show that this polynomial has at most 2 real roots. You know what you're going to do. What are you going to do? Assume there are 3. Exactly. Assume there are 3 and come up with a contradiction. Let's give them names, A, B, and D. And let's list them in increasing order. Your thoughts? We're going to apply Rolle's theorem to the interval AB and to the interval BD. And Benjamin is asking, can't a degree 4 have at most 4 roots? Correct. And you can prove that using Rolle's theorem. So shouldn't we prove 4 roots instead of 3? Well, that's the thing, right? I mean, in general, a polynomial of degree 4 can have up to 4 roots. Here, though, the claim is that this family, this special family, which have this form, are going to have at most 2. I claim some would not have any. If C is too large, this won't have any roots. But let's show that we don't get 3. And of course, if you don't have 3, then you don't have more than 3, right? Because if you had 4, then you would have had at least 3, and you could repeat this argument on those 3. So we're going to apply Rolle's theorem twice to the interval AB and to the interval BD, where P of X is continuous on these and differentiable on the open interval. Right, it's important to mention that this function satisfies the hypotheses, right? Because it's a polynomial, so you know it's continuous and differentiable everywhere. Very well. So apply Rolle's theorem to the interval AB. What's the conclusion? Since P of A is equal to P of B, well, in fact, they're both equal to 0, by Rolle's theorem, there exists, let's call it C1 in the interval AB, such that P prime of C1 is equal to 0. Oh, buffering already? Jeez. Well, yesterday we buffered, I think, 3 times. First one around noon. And then again at the usual 12:36 or something. We'll see. How do we know that P of A and P of B is 0? Because A and B are roots. Also, P of B and P of D is 0. So by Rolle's again, there exists an element C2 in the open interval BD, such that P prime of C2 is 0. All right, so you see, we have 2 values, C1 and C2, 2 different values, right? Because these intervals do not overlap. Right, so we have 2 points, C1 and C2, where the derivatives are 0. Well, what is the derivative? P prime is what? It's 4x cubed plus 4, which factors as x cubed plus 1. And I mean, you can spot a root immediately here. X equals -1 is a root. So x plus 1 has to be a factor. And I'll let you do the long division, but I'm sure you've done this enough to know that it factors this way. Is that right? X cubed minus x squared plus x squared, that cancels out. Plus x minus x, that's gone as well. There it is. And here, what are the roots of this? According to the quadratic formula, negative b plus or minus square root of b squared minus 4ac over 2a. No real roots. So you see what's going on, right? The derivative is only 0 at -1. The derivative is only 0 at -1 -1 contradicting the existence of C1 and C2 There it is. That would have been fine as well, Sealan. Yeah. But this is better. Kamal's asking why we find the roots of the derivative. Well, the conclusion to Rolle's theorem tells us the derivative has to be 0 at 2 different places. So let's see if that really happens. We find the derivative and we see that it is equal to 0 only at one place. All right. Questions? Maxwell is asking why we don't solve for the original equation equal to 0. Well, I mean, you go ahead and try to solve for that. You don't even know what C is. And the question isn't asking for us to solve for that. It's asking to show that there are at most 2 roots. So what we showed was we assumed we had 3 roots, A, B, and D. And we applied Rolle's theorem to the interval AB to get a point where the derivative is 0. We applied Rolle's theorem to the interval BD to get a point where the derivative is 0, right? So the derivative is 0 at 2 different places by 2 applications of Rolle's theorem. And when you look at the actual derivative, you see that it's equal to 0 only one place, only at x equals -1. Well, it's not that we failed. It's not that we failed. It's that this particular derivative only has 1 root. But by assuming we had 3 roots to the original function, Rolle's theorem gave us that the derivative must have had 2 roots. And this is a contradiction. The derivative only has 1 root, not 2. So an assumption we made must have been wrong. And the only assumption we made was that we had 3 roots of the original function. Exactly that. On an exam, you have to justify everything. You have to write exactly what I wrote down here. Right? I mean, you have to explain to the marker as I'm explaining it to you now. as you would explain it to somebody who doesn't know anything. You have to explain it in a way that it makes sense and that whoever you're explaining it to can understand it. Well, I mean, let's not. So, user is asking if we had assumed there were 4 roots. The question is showing there's at most 2 roots. So there's no reason for you to go to 4, because if you had 4 roots, A, B, C, D, then you would have had to have 3 roots as well. Right? So there's no need to go to 4. And in fact, if you show that there are not 4 roots, well, there could have been 3. And then you're in trouble. Because the question was asking you to show at most 2. But by taking 3, if you show there cannot be 3, then there have to be at most 2. Right? And if you had 4 to begin with, then for sure you also have 3. Could you show us an example like that? I don't know an example like what. But I mean, look, the book has plenty, and it's always the same argument. Well, as far as this course is concerned, it's always the same argument. Let's look at this. Show that where there is 3 roots but not 4. That's not going to happen in a polynomial of degree 4, right? So you're going to need to go higher, probably polynomial degree 5 though, unless you restricted your attention to a particular interval. That might happen as well. Shamira, what are you saying? Sign of 0, 0. That's right. And? Oh, you mean the strict inequality? Sorry. This was not closed. Thank you. Absolutely. Absolutely. You're right. You're absolutely right. Consider this. And before we prove it, let me point out, right, if you bring the x to the other side here, this is kind of half the squeeze theorem if you take a limit as x goes to 0. Right? This would show that the limit as x goes to 0 of sine x over x is less than or equal to 1. So a very important limit that we saw when looking at the derivative. So let's prove it. It's a nice final exam question. right? What are we going to do? We're going to define a function and maybe apply the mean value theorem. So let's define the function sine t. And for x in the interval 0 to 2 pi, right, fix an x in here and apply the mean value theorem to the interval 0x. Are they though? Are these final exam questions so much better? I mean, I think your midterm questions were very doable. No? How was the midterm, by the way? Did we never discuss that? Did we discuss that? Too easy? All right, well, it's a mix. Well, yeah, so I mean, I think I did mention that, I mean, it's easy to spend more than 3 hours, but that's because you have that opportunity. Well, your TA. Exactly, right? The last few questions were very easy. Well, if it was an in-class exam, we wouldn't have done those variables A, B, C kind of thing. There wouldn't have been need to do that. And again, you don't know anybody who did it in under 6 hours. That's because there's no reason for you to do it under 6 hours. But if you had to do it, then you would have done it. All right. Well, look, I mean, let's not worry about it too much. It's over. So what are we doing here? We've defined a function and we are applying the mean value theorem to the well, like I said, I mean, if this had been an in-person exam, it would have been different. Yeah, I think the midterm is 30%, but we have announced an alternate grading scheme. Has that been announced on my courses? Let me say this, Danielle. Danielle says she didn't know how much she should explain. You have to explain everything. Absolutely everything. So you have to show all work, justify every step. And that's going to be the same on the final. Show all work, justify every step. Well, I mean, of course not. If you say the limit of a sum is the sum of the limits, you don't have to justify that, but you have to show the step. I mean, look, certainly these online classes are taking its toll, and yeah, it's the same for everybody. Do we have to prove continuity? Well, I mean, let's take the few examples we showed. Well, in fact, right here, right? I'm defining this function f. I don't have to prove it's continuous, but at least I should state it, right? We know f is continuous on the whole real line. So that is continuous and differentiable on the whole real line. So in particular, on 0x and 0x respectively. Right? On an exam, you should mention that. Yeah, what wasn't there? Didn't Sean announce an alternate grading scheme? No? So let me, all right, then let me not announce anything immediately then, but there's going to be an alternate grading scheme for those who did not do well on the midterm. Let's postpone any announcement of the sort until next week, but we're working on something. Right, so while you don't have to prove f is continuous, respectively, right, your function is continuous and differentiable on all the var, so continuous on the closed and bounded interval 0x, and differentiable on the open interval. All right. And what is the conclusion? F of x minus f of 0 over x minus 0 should be the derivative for some c in the interval 0x. But what is this? So this is sine x minus sine of 0, which is 0. And the derivative of sine, you know to be cosine. All right. And since c is in the interval 0x, and x is in the interval 0 to 2 pi, then this is in the interval 0 to 2 pi. And you know the graph of cosine, right? In the interval 0 to 2 pi, cosine is 1, but it's 1 at 0 and it's 1 at 2 pi, and everywhere else it's strictly less than 1. So if you remove these two endpoints, this is strictly less than 1. So sine x over x is strictly less than 1. And since x is positive, if you multiply the whole inequality by x, the inequality is maintained, and we get sine x is less than x. Exactly what we wanted to prove. Liam, we do round brackets do not include the endpoints. And that's why it's less than 1, right? Cosine in the interval 0 to 2 pi, cosine is 1 at 0 and at 2 pi, and everywhere else it's strictly less than 1. And there it is. Y is it equal to cosine of c? This is just the mean value theorem. Right? We were applying the mean value theorem to the interval 0x. So to f on the interval 0x. Let's do one more. Let's prove this trig identity, if you will. And when we were reviewing trigonometry, the question arose, I believe, how can we prove some of these identities? Well, you're going to be able to prove some of them in exactly the same way we're going to prove this right now. How are we going to prove this? Let's define a function. Arctan x plus arctan of 1 over x. Let's take the derivative, see what happens. Are you still there? There was a slight dip in electricity. We could have gotten disconnected. Very good. Thank you, Michael. While we're here, let me mention that should ever that happen, if we ever run out of electricity, there's a power shortage or something, stand by. I will either it'll come back quickly, or I'll make the necessary arrangements to get back online as soon as possible. So take the derivative. Take the derivative. What is the derivative? You know the derivative of arctan. 1 over 1 plus x squared. So the derivative of arctan of 1 over x, that's going to be 1 plus 1 over x all squared, times the derivative of the inside. Chain rule, right? And we get a minus 1 over x squared. Well, let me put the minus out front. Now let me multiply x squared, the whole denominator, by x squared. And what do we get? We get x squared plus 1. Which is easily seen to be 0. Well, that's unexpected. Perhaps. Perhaps not. What does that mean? If the derivative is 0, then the function had to be constant to begin with. Exactly. Very nice. Right? I mean, we saw that result. If the derivative is 0, your function had to be constant to begin with. So your function, artan x plus artan 1 over x, has to be constant. Take any value you want, plug it in, any value bigger than 0. So if x is 1, you get artan 1 plus artan 1 is c, but artan of 1 is, you know what it is. There it is. Very nice. And now you can try to prove some trig identities in the same way. Right? If you have an equation relating to trigonometric functions, this is only for x bigger than 0, correct? What's going to happen if x is less than 0? Do you see it? Well, it's not that it proves the given domain, it's that this equality is only valid when x is bigger than 0. Why is x equal to 1? It doesn't matter what value of x you choose to find the constant. So in particular, if x is 1. Because you know the value of artan of 1. We did not prove x had to be bigger. Nothing wrong with choosing 2. But what is artan of 2? Right? I mean, everybody's correct that it doesn't matter what value you choose. We're back, thank you. 1 is just more convenient because you know what artan of 1 is. If you chose 2, what is artan of 2? I don't know. What is artan of 1/2? I don't know. If you chose, what could you have chosen? You could have chosen root 3, right? Root 3 would have been another good choice. Pi. Well, would it? I mean, I don't know what arctan of pi is. And even arctan of pi. Arctan of pi, I don't know. So all those values will give you pi over 2 in the end. Absolutely. Even those that you cannot evaluate, like arctan of 2 plus arctan of 1/2. I don't know what any of these things are, but when you add them together, you have to get pi over 2. And as somebody mentioned, if you were restricting your attention to the other half, x less than 0, you could have plugged in -1, and you would have gotten negative pi over 4 here, negative pi over 4 here. So the constant would have been negative pi over 2. See, Lynn, it's not that we're proving it only when x is bigger than 0. The question is telling us to restrict our attention to that. And as Matthew points out, if x is less than 0, it's negative pi over 2. Okay. So the question is right? Look, you see there's a problem at 0, right? When x is 0, this is undefined. So, of course, you need to restrict your attention to values bigger than 0 or to values less than 0. The question is telling us to restrict your attention to values bigger than 0. So that's why when I'm trying to figure out what C is, I'm going to restrict, I'm going to choose whatever value you want to choose, as long as it's bigger than 0. And as long as it helps you evaluate what C is. Let me just point out, if you had chosen x equals root 3, what do we get? We get arctan of root 3 plus arctan of 1 over root 3. But you know arctan of root 3. Right? You know that tangent of pi over 3 is sine of pi over 3 over cosine of pi over 3. Sine of pi over 3 is root 3 over 2. Cosine of pi over 3 is 1/2. So arctan of root 3 is pi over 3. And tangent of pi over 6, which is sine of pi over 6 over cosine of pi over 6. This is 1/2 over root 3 over 2, which is 1 over root 3. So arctan of 1 over root 3 is pi over 6. So your C has to be the sum of these two, which is 3 pi over 6, which is pi over 2. So it doesn't have to be 1. Root 3 works as well. And 1 over root 3 would have worked as well. And so on and so on. How are we doing here? Questions? Anybody? Seems like a good place to end. We've done more than enough for the day. Thank you all for coming. You guys have a good weekend, and I will see you on Monday.